Let's graph the polynomial h of x is equal to negative 2x squared plus 11x minus 12. If we're going to produce a sketch of this polynomial, we're going to want to identify three key characteristics. The first is we want to identify the end behavior. The second, we want to identify the y-intercept. And third, we want to identify if the polynomial has any x-intercepts. For the end behavior, we look at this dominant term right here, this first term when the polynomial is written in standard form. We have an even degree and a negative coefficient. Using our end behavior analysis, we know that the ends of this graph are going to look like that. And we should anticipate when we draw it that we will see the falling on both sides of the graph. Our y-intercept will always start with x is equal to 0. If x is equal to 0, both the first term and the second term go to 0, leaving us with the constant term of negative 12. Identifying the x-intercept is going to be a little bit trickier. That's going to require us to set the polynomial equal to 0 and solve. We want to make the factoring that we're going to need to do a little bit easier on ourselves. So we're going to factor out a negative 1 from the polynomial. That changes all of the signs on the inside of the polynomial. This trinomial right here is a candidate for the AC method. So we look at the AC method, we see we want a product of 24, but we want a sum of negative 11. Our two numbers are going to be negative 8 and negative 3. So that's how we will split our middle term into negative 8x and negative 3x. Common factor for the first two terms is 2x. We want that binomial to match, so in order to do that, we need to use negative 3 as the common factor out of the back half of the polynomial, leaving us with 2x minus 3, and then the common binomial of x minus 4. No need to worry about this negative 1 or this negative sign that's outside of the bracket. That's not going to ever create a 0. The only way that this polynomial will ever be 0 is if either one of those is ever 0. Two ways for that to happen: x is equal to 1/2 or x is equal to 4. And that's our two x-intercepts, 4, 0 and 1.5, 0. We move to our graph and we identify 0, negative 12 as our only scaled point. Whoops, I ran out of room. Or we'll put it down here. As our only scaled point on the y-axis. We have two x-intercepts. One of them is at 1.5. The other is at 4. Based on the information that we have, we know the end behavior of this polynomial is the falling on both sides. So out of the rightmost point that we have, we would expect it to be falling. Out of the leftmost point that we have, we would expect it to also be falling. And in between those points, we're in a little bit of a tricky situation. We know we have to get from this y-intercept up to that x-intercept. So we're going to draw this as best we can up to here. And then we know that we're going to cross through that intercept and cross through this intercept. So my only option is to have some kind of maximum in between the two of those. Now, as the polynomials get more and more complicated, the potential exists for there to be minor little variations, bumps along the way. Polynomial sketching as a skill is more about, can you get a rough visual of the idea? This is what the polynomial actually looks like. Here's our intercept at 1.5 and 4. Here's our y-intercept at negative 12. Did I guess that the x-intercept, or excuse me, not the x-intercept, the relative maximum right here was at roughly 2 to 2.5, something in there? No, I did not. There are ways of finding that point, but we're just going to give a rough sketch. You'll notice symmetry in a polynomial, especially with the parabolas. Symmetry is a good skill to exploit in trying to draw them as best you can. But sometimes you're not going to be able to identify exactly where those points are, and that's okay. Polynomial sketching is just about giving a rough idea of what a polynomial is going to look like based off of these three key characteristics.